Good morning, everyone. My name is Ian. As Vincent says, I'm over from PyData London. I'm so proud of the community that we built there that I'm still wearing the t-shirt from our conference last month. If you ever come to London, you're very welcome to come and join our monthly meetups and the annual conference that we run. So here I'm going to be talking about creating correct and capable classifiers. I like my alliterative titles. I particularly like debugging my machine learning and understanding why it's doing what it says it's doing, such that I can explain it to other people and such that I can be confident myself. So I'm an engineering data scientist. Unlike a lot of data scientists, I don't have a PhD. I didn't go down the formal academic route. I had a master's degree and then joined the startup world with dreams of glory, avarice and early retirement. And of course it went way, and all went wrong. And I thought, hey, I should go and do a PhD. And then no, I joined another company, then started my own company. And it kind of goes around. So I've been an engineering data scientist for 15 years, kind of making it all up as I go along. And as a result of that, I ended up writing a book on high-performance computing with O'Reilly several years ago, with a US colleague, Misha Gorolik of Bitly at the time. And along the way, I've built several communities, and the one that I'm really proud of is this PyData London. We're like 7,500 members in London now, and it makes it the largest PyData on the planet, which I'm super happy about. And I'm particularly happy that last week, the PyData group globally, we got to 100 meetups around the planet. So our PyData community it's not just like a bit global, it's properly global, like it's 3 digits now. This is great, and we're going to keep growing. So I work with all sorts of companies, both small startups and large organizations, Mitsubishi Finance Bank, Channel 4, QBE is an insurance company I'm working with at the moment, introducing machine learning and then using these kind of techniques on the ground to help communicate this work with colleagues. Before I get into the talk, there's a point that I've been increasingly making over the last several years. Many people who come to these conferences see them as commercial events and they forget that they are mostly volunteer driven. So the NumFOCUS group behind this puts in tireless work around the world to promote PyData. All the PyData organizers, they're typically all volunteers in London. I've got a 13-strong volunteer group, 3 chairs for the conference this year, all volunteers. I've been volunteering for 5 years, been building this all up. Everyone here in Amsterdam is a volunteer. So if you're not used to going up to volunteers and saying thank you, today's a brilliant time for that. You just have to go up, find a speaker or any of the volunteer organizers and just say thank you. That's a lovely thing to do, to say thank you for the volunteering work they're doing to bring us this conference. Even better, you can buy them a beer or some cake, or a cup of coffee, but just say thank you. It makes the world a better place, and it recognizes that everyone running these events are not paid, they're all volunteers. Back in London, I forgot to take a photograph of my audience. I love taking photographs of audiences. I would like to take a photograph now, given GDPR and personally identifiable information. I've read up this morning, thanks to Michelle, on the Wikimedia Commons rule interpretation for the Dutch laws. I believe I can take your photograph, but I don't know. So I'm going to say, if anyone objects, I won't take a photograph. Does anyone object? And it's totally cool if... I'm not going to ask for explicit consent. I'm just going to say if anyone objects, I won't do it, because that's like a common politeness thing. And if not, no objection. All right, brilliant. In that case then, please smile and wave at me, because I just like a happy photograph. So smiling and waving, that means hands up, hands up. All right, that's better. Brilliant, one of those. Another one, and another one. Excellent, thank you very much. Yeah, I don't quite know what the situation will be now for taking a photograph at a private event in a non-public space, because that it apparently requires explicit consent under some interpretation. So I don't know. Anyway, it'll be on my blog, non-commercial use. It's just on my blog. Right, goals today. We're going to talk about getting a baseline model in machine learning, so something that we can work from to improve against, rather than diving in with the most complex model we might come up with, which is an approach taken by some people. Visualizing errors and diagnosing areas of problem in the machine learning model. Is it data-driven problems? Is it a machine learning driven problem? We'll look at explaining decisions, and I'm one of 2 speakers at least talking on that this weekend here. And then if you want more, then I've got a GitHub account to my data science delivered project I've been building up for several years. That's a pile of documented advice, kind of advice to myself from 10 years in the future, stuff that I wished I'd known 10 years ago when I was starting this, along with a whole bunch of worked notebooks which go through various examples. And the examples for this talk will be online in the next week or so. So first of all, who knows pandas profiling? Has anyone come across this? A smattering of hands, not many hands. Brilliant, right, there's your first tool. First tool for the day. So pandas profiling gives you a really easy one-line way, this .profile report, to summarize the contents of a data frame visually with some JavaScript in your Jupyter notebook. So it's a really easy way of getting an overview of data that you've got. It tells you some things about the data set. Here I'm using the Kaggle Titanic example because most of us here will know Titanic. It tells you about the contents of the data frame. So it's just like looking at a describe and info output from a pandas data frame, but visually. And there's a few more interesting bits. One bit that I quite like is the warnings. It tells you things like, oh, this age column has got 20% missing values. Oh, it's kind of interesting. I could do that by hand, but here I get this automatic summary. Cabin has high cardinality, so 148 distinct values. It looks like not a very useful field for doing, say, machine learning. And then some columns, age imputed, has very high correlation with another column, the age column, and so it would reject it from the analysis done inside here. So maybe this gives you an early warning about high correlations and redundant data in your data frame. It also gives you a breakdown by tabs of all of your columns, and you get things like, say, for the age column, you get a really nice histogram giving you just the distribution. All of the descriptive statistics that come out of the info and describe functions laid out. And then for columns that are categorical in nature, like the embarked column, we also get another set of displays. So these are broken out on a bunch of tabs. And then there's correlation matrices that come out as well. So if you're starting a project, you've got new data, you don't know what's in there, put it through pandas profiling, you get a really good idea as to what's in your data set. Then we're going to start. So we've done that. We've got an idea about our data. Now we want to think about building a dummy classifier, this first thing that we're going to do. So here I'm going to use the scikit-learn dummy classifier. Hands up if you've used the dummy classifier and the dummy regressor before. Not enough of you at all. Right, so rather than starting with a complex machine learning model, diving in with XGBoost or like GBM or whatever you think is appropriate, I always, for myself, and I always recommend, going in with a very basic approach. The dummy classifier says, in this case, what is the most frequent answer in the data set? And then every prediction I make will be the most frequent answer. So it's really dumb. It's an if-then-else rule that makes one prediction all the time. So it's absolutely wrong a chunk of the time, and absolutely right more of the time. It's really stupid, but it gives you a baseline. So you can't do you shouldn't be doing any machine learning. You shouldn't be doing any worse than this. But if you don't have a baseline, you don't know. So if we put this dummy classifier, about roughly 60% of people died on the Titanic, and so 40% survived. So if we split our data, X and Y trained test set, on the training set, we say, what is the majority decision? Did people mostly die or mostly survive? Well, they mostly died, so we always predict that everybody dies. And then when we score on the test set, we're right about 60% of the time, and then wrong 40% of the time. But at least we've got a baseline now. I've seen people dive into problems with really complex classifiers, doing loads of work on their feature engineering, and they come up with an answer. Isn't it brilliant? They go, yeah, right, but if we take that output column and just take the mean of it, which is kind of what this is doing here, we get the same answer. But you've spent 2 months building a really complicated way of predicting the mean because there's no signal in your data. So doing this 5 lines, really easy. Now, if we run this again on another data set, so another train test split, the same decision will be made, the same predictions will be made, but the score will be different because that test set is varying. So if we do that lots of times, we get a distribution of scores on different test sets. And even though we're predicting one thing, the majority outcome, everybody dies, because these train test splits are different every time, we get a different number of people surviving and dying between the train and test sets. And this distribution, when we draw it, we get some idea of the variance in our predictions. So if you just ever take one train test split and you build up your model and you get your answers and you're being very careful, you're training on your train set, you're just observing the test set, and you think, hey, this is generalizing really well. If you then take another train test set and you find your numbers vary, it's because of this variance in the underlying distribution of data that we're working from. You do it many times and you think, hang on a minute, I get scores from 55% to nearly 70%. That's a pretty high variance for the dumbest possible decision. So how much do I trust any one answer that I get? And that's a good question to bear in mind. I always suggest eyeballing the underlying data. One of the common approaches to fixing missing data is to impute. And on the Kaggle dataset for Titanic, if you go into the forums, everyone says, oh, the age column, it's missing age data a bunch of the time. So the statistically relevant way to fix this is to impute the median value or the mean value or some other made up notion of fixing data where we've lost the true answer. And then typically people don't graph this, and so they don't really know what distortion is occurring in the data. If we look at the non-imputed data set, we see that there are a few very young people, that's the most left-hand column, most people around sort of 20 to 30 years old, and then some people go up to about 70 years old. If you take the 200 NAN rows and impute them to the median, you get an imputed age of 28, and then when you stick that back onto the data, you end up with this huge spike. Apparently another 20% of your data set have suddenly become 28 years old. But it's a lie, right? We just made this up. We made a statistical guess about a thing and filled in this missing data with something else. I've gone back to the original records for some of the Kaggle, the Titanic passengers, and checked if they had an imputed age of 28, what their true age was. And their true age could be 10 or 50. It's all over the place. So imputing without observing is a bad idea. But at least if you've drawn it, you've got an idea, and it might help you to debug things later in your project, or possibly later in the slides that we show this morning. So we've built our baseline classifier. We've got something really simple. We've done a number of runs, and we've got an idea of variance by drawing a distribution of answers. We've eyeballed our underlying data. We've fixed some of the data. We've got a pretty good idea as to what's going on. Now it's time to use a more sophisticated classifier. So typically I'll just go for a random forest. If I had lots of missing data, I might use XGBoost, but random forest works super reliably with all the tools in the wider scikit-learn ecosystem. So we train up a bunch of results on train test splits. Here I'm using the repeated k-fold cross-validator. So that does, I think I did 5-fold cross-validation, repeated 20 times, I guess. So I got 100 folds worth of answers, and I can get a distribution out of this. So rather than having a for loop doing this many times, repeated k-fold does that for loop for you internally. And then you get lots of scores back, and you can make a distribution. You look and think, well, okay, it might be better, it might be worse, I don't know. I haven't changed my my axes yet to make this comparable to the previous result. But I've got scores from 76% up to nearly 90%. That's way better than I had before. And then if we draw them side by side, we can see that we've got two distributions. The left-hand one is the dummy classifier. The best result from the dummy classifier is worse than the worst result from the random forest. So these distributions are clearly separate. All of these answers are better than all of those answers, regardless of the split in the data that we had. So we can be fairly happy that this is a better classifier. At this point, we can start hyperparameter tuning and twiddling around with different algorithms and trying lots of things and trying to make the mean slightly better than the previous mean. And that's the way you win a Kaggle competition. But if you start drawing those distributions of the new classifiers over the old distributions, you might well start to find that they all just kind of look the same. And then within the variance of, within the bounds of the variance, the natural variance, and noise in those splits and in the models, that actually these distributions are the same thing. So these models that you're making with these slightly higher mean values aren't really any better than they're not really differentiable from any of the others. So I always recommend just drawing the results of all of your experiments. And when your gut says, hey, this is not getting any better, just stop and don't worry about it. Don't obsess over hyperparameter tuning and the like. You don't tend to get very far. Who's used the YellowBrick module? Okay, again, only a couple of hands. Right, another great tool for you. YellowBrick, this was introduced, or at least as I understand it, the PyData introductory video was at London a couple of years ago, and that's when I learned about it. Rachel Bilbrook, I think. YellowBrick takes a bunch of the example code on the scikit-learn website for how to visualize your model answers and makes a really simple couple of line interface so that you can easily visualize your scikit-learn answers. So it's just a glorified wrapper for a bunch of examples that come off of the scikit-learn website, and then more has been added over time. Confusion matrix is a great way to diagnose the quality of your classifier outputs. So we can see our true negatives in the top left-hand corner. This is off the random forest classifier. True positives in the bottom right corner. And then we can see the errors that are being made. And there aren't so many errors that are being made here. And then a typical way to proceed is to think about this, tweak your model parameters, and then see if you can shift the error numbers into their correct quadrants, move them around, so you have more truth and less error. And of course, you can't fix all of it, because these classes typically are never fully not differentiable, what's the word I'm looking for? Separable, thank you, that's the word I'm looking for. So they're not fully separable, so there will always be some level of error in there, and the errors vary between the type of model that you're using. So this is a way of looking at errors in your data, but it's not really insightful, it doesn't get you very far. So one thing I've started to mess around with is this is my visualization, take the same splits of the data, but rather than just counting the number of true negatives and true positives that we had, instead drawing the underlying probabilities that come out of the classifier. If all of your probabilities for your true negatives are over towards 0, so the classifier is pretty darned confident that this person really didn't survive. Their probability of death of survival is very low. And here, if their probability of survival is very high, then I'm pretty happy that the classifier is very confident in its decision making. If it were the case that all of these counts were up towards, let's say, 45%, so it's this person definitely died with a 45% likelihood, or sorry, 55% likelihood that they died. And if the true positives were close to, say, 55%, just over the decision boundary, although the binary decision that we see in the confusion matrix is true, the actual, my confidence in the classifier's decision would be pretty low. So this gives me another way of beginning to dig into the probabilities behind things. YellowBrick lets us look at the ROC curve as well. I was a bit conflicted about putting this in here. ROC curve comes up in all the tutorials. You must draw a ROC curve to show off the area under the curve. And then you compare the ROC curve here for, this is the random forest, and that's for a logistic regression that I ran. And sure enough, the AUC is a bit lower, 87% here than 90% for the random forest. I'm not really sure what you get out of a ROC curve visualization. It's a bit of a pain to do it, given the code on the scikit-learn website. YellowBrick makes it really easy, so I thought it was worth including. If anyone here has actually made hard decisions using an ROC curve, I'd be very keen to hear about that afterwards. Put up your hand, in fact, if you find really strong value in an ROC curve as a diagnostic tool. It's in all the books, it's in all the tutorials.
So, well, I like the decision recall curves usually.
Okay, right, yeah. So precision recall curves are also in YellowBrick. I put this up just because it's kind of covered everywhere, but then I just thought, why? What value do I get out of this? So if anyone has feedback for me afterwards, I would love to hear it. Because yeah, I'm not sure about that conventional wisdom. Okay, so now I want to start really drilling down into what my estimator is doing. So one of the ways that I start to do that is I take the underlying probabilities, so the truthy values, the probabilities from the classifier, and compare them to the truthy values, and I calculate errors. I want to see particularly which things it's mispredicting the most. So when it should predict 0, but it predicts 1, so maybe it predicts 99%, so that'd be a 99% error. Now when it should predict a 1, and it predicts close to a 0. So I want those largest magnitude errors. So you can calculate your errors and then sort a data frame by size of error, and in this case I filtered for people who did survive, and then it predicted that they died, so there was a very large error, and I get the underlying probability from the estimator, and I've got the passenger ID, at which point I can match that data back against the original data that goes into the learning process, and here I've used the pandas style function to put some colors behind this, so we can see those same passenger IDs coming through. We can see that is female is false, so all of these people who were mispredicted were male from the passenger manifest. Their siblings, spouses, parents and children counts, the size of their family is very low, typically 0. The fares are very low as well. They've got a mixture of ages, but in this case all of them should have survived, but they were predicted to all have died. So I can't diagnose anything from this particularly, I don't think, because this data, the underlying data here, I trust. When I do this on a client problem, typically all the miscodings in the data just jump straight out. And I can see numbers that are strings or dates that are back to front or things that are misrepresented, things that are clearly coded wrong. All of it jumps out in this display. So this is a brilliant first way. You build a model, you do a little diagnostic, all the rubbish just leaps into your face. So that's kind of nice because then you've got a way to go through and begin to fix the underlying rubbish. You can then split your errors by some kind of significant feature. So if I've looked at, say, feature importance or permutation importance behind my estimator, and it tells me, oh, P-class, whether they're first, second, or third class, is an incredibly predictive feature. I think, okay, right, so what if I split out all of in the test set, split out all of the first class passengers, and then compute some accuracy metrics around only first class passengers? And what if I do the same for second-class passengers? So we get some precisions, recalls, and F1s that are pretty good for the first-class passengers. This is on the test set. We've trained on first, second, and third class, the whole data set. Then on the test set, we've split out just the first class, and we're computing these metrics just from the first class. That's pretty good. Take just the second-class passengers out, and those results are better. So for some reason, second-class passengers with respect to this data and this estimator are easier to predict. Now, that might be the estimator is somehow better at this data set. It might be the data's cleaner for second-class passengers. It might just be that second-class passengers were easier to separate in this data set. It was more likely you could figure out if they were going to survive or going to die. But this gives you another way of diagnosing your data. If you're not convinced by the way you split your data out and which bits the model says are easy to predict and which bits are hard to predict, you might want to go back to your data or revisit your understanding of the problem to think about whether you really trust these results. Here's a crazy idea I've been developing recently. You might tell me it's bonkers. That would be great feedback. You might tell me it's useful. Tell me afterwards and give me your thoughts. One thing I've been curious about is if I start splitting my data out by a major feature like P-class or the sex of the passenger, I'm imposing a constraint upon the data. I'm saying I think these things distinguish things that we can predict and these things that we can't predict and where the errors might lie. So I'm imposing my own knowledge upon the problem. What I really want is the data to bubble up in some kind of unsupervised magic way, which bits of the data I should be paying attention to. So I've developed this as a first idea. It could be stupid, but you tell me. If I use tsne, a dimensionality reduction technique that is built into sklearn, I can group all of the passengers that are similar by features. So I'm not grouping by the survived column. I don't want to put the target variable into this set. But for all of the other features that go into the machine learning, the thing that you learn the relationship from, the X values, I put those into tsne. It projects this high-dimensional, continuous and categorical feature space down to a two-dimensional plot. So any dots that are close to each other are passengers whose attributes look similar. That's it. And if they're a long way from each other, then those attributes look quite different from each other, according to tsne. I've then drawn it with crosses if they didn't survive and circles if they did survive. So I've taken that extra column that I wasn't using in tsne and used it to enhance the diagram. So I didn't go into the tsne, that was used to enhance. I then color by absolute error. So we look at the things that it predicts correctly and the things it predicts wrongly. If absolute error is small, and it's a cross, then the person did die and the model predicted that accurately. So the error was small. If the absolute error is high, so close to white, and it's a circle, then the person did survive, but the model predicted that they did die very confidently, so the error was large. And then we get some interesting patterns popping out. So we get a bunch of dark crosses here. So these all kind of look fairly consistent. Most people died and the model said they did die correctly. And then we get some areas where you get a mixture of crosses in red. So this is people who died and the model got it correct. And circles that are bright. So this is where people did survive, but the model said they didn't survive. So what if we then start to look at the passengers represented by these coordinates in the tsne to get back to the underlying features? Then the model is telling me in this unsupervised way which things look like they look similar, and we've got these conflicted areas in the decision space. So if I pull out the things that look similar, where the predictions were all good, we see they're all third-class passengers. They're typically all male. They've got small families. They didn't pay a lot. What's funny about the age imputed column? Now, I don't know if that's a thing. You know, that didn't seem to influence the decision. All of these predictions, all but one of them are correct. So, you know, it did a great job. Maybe this age imputed doesn't really matter here, but it's a little bit suspicious to me that when I pull out a region of space that the model says looks kind of similar, and I find it's full of people who've got the same imputed values, the same missing column. That's kind of weird. Maybe I'd want to dig further and see if I really trust the data behind that. And if we look at a conflicted area, this is that second region of space, I find lots of first-class passengers where it's female is false, so they're male, small families. Age imputed is also pretty much full of 28s. And if you go back to the source of truth from the Titanic manifest, you see that these ages are all over the place. And if you put in the truthy ages and make a reprediction, you get a very different prediction than the one that we get here, which suggests that if you were to fill in this data that's missing, you could get a better result perhaps. So I think that's kind of an interesting diagnostic technique. You might tell me it's not, so I'm curious about your feedback afterwards. And then finally, a couple of slides, I'll just wrap up. Who's used Shapley explanations before, the Shapley tool? Anyone come across that? It's pretty new. It's presented at NIPS a year or so back. It's one of a set of explanation tools that have been developed recently. 10 minutes until I need to be off stage. Okay, it's fine. Yeah, I'm at 5 minutes. That's great. I'm all good. Shapley is one of 3 techniques for explaining your models. 2 other techniques, Eli 5 and Lime, and they're being covered in a talk tomorrow. So Shapley, as the paper presents itself, is a game-theoretic optimal solution to the other 2 approaches, which gives you everything. It's the one explanation technique that rules them all, apparently. I'm not quite sure I believe that yet, but it does feel more powerful than the other 2 approaches for continuous space problems. So with the Shapley explanation, I can do several things. I'm going to show you, I think, 3 of them I'm going to show here of the 4 things it can do. If I take a single prediction that I want to explain, so passenger ID 231, the truth is 1, so this person survived. I can look at the underlying features just from my data, and then the question is, well, how do these features contribute to the prediction for this person survived? And then the Shapley explanation, this is a nice bit of D3 JavaScript in the browser, we can get the numbers out, says, well, it was roughly the case that 40% of people survived. Because this person had a FAIR of 83, which is pretty high, that had a significant increase in their probability of survival. Because they're first class, that had a bigger increase in their probability of survival. And because they were female, it had an even bigger increase in their probability of survival. And when you sum those bits together, you get a number that's 1, so 99.7%. You get a 100% probability of survival given these particular attributes. So this is a way of explaining, given all of the other examples that are around, and it's based on a model based on all of the test set data that's available, explaining individual predictions. If we put in a different example, passenger ID 635, truth is 0, they died. The model says they died. So the model's an agreement, which is brilliant. This is my random forest model. These are the attributes. If we put those into Shapley, it gives us a slightly different display. It's saying, well, about 60% of people died. Given that, the fact that they had a larger than usual FAIR decreases their probability of death. The fact that decreases their probability of survival. The fact that they were third class decreases their probability of survival even more. The fact that they had a larger family decreases their probability of survival even more. But because they were very young, age was 9, and because they were female, so they weren't a man or a woman, that increases their chance of survival. And if you sum all of those bits together, you get an explanation of 0.06, which is very close to this explanation here. So you can then start to pull out the underlying features that drive the decision. Now, you might not like those decisions. You might sit back and go, well, that's a pile of rubbish. What's going on there? That makes no sense. Then you have to ask yourself, well, is the model overfitting? Is my data straight? Is my understanding of the underlying problem good? So I'm using this in the insurance industry as we try to explain the predictions behind some of the riskiness of certain assets and then how you price those particular policies. And this means that I can take my incredibly rich black box model, which gives a great result, and none of us really understand how it works because, hey, you've got a 1,000-tree XGBoost model with a 1,000 wide feature set. What the heck's going on in there? But I can break out the most important contributors to the final regressed decision, and it works for regression as well, and then explain what those contributions are. And the business owner goes, oh yeah, that kind of makes sense, that makes sense. yeah, I kind of like that story, and that's nice. Or when the data's guff, then they turn around and go, that doesn't make any sense. And I'm thinking, yeah, it's because I can see the data that's broken. Those numbers shouldn't make any sense at all. So I find this very useful as a diagnostic. Shapley also groups together all of the similar predictions by similar features. So this is not a million miles away from that T-SNE diagram I showed. Here, example 34 is the one that I showed on the previous slide. It's a first-class woman who paid a fair amount of money and got a 97% or 99.7% prediction. If I look at the next example along, number 36, very similar attributes, but a different count for the family size and a slightly lower probability of survival as a result. So you can start to scroll back, and it's a nice interactive interface. You just scroll back and forth. You can see people who it predicted survived or died, and see what the contributions of all the individual features were. And a final thing that it can do, if you take all of the examples in your test set, and then you start saying, well, what contribution does the is female indicator have if everything else is held constant? So which features kind of feel predictive, and in what way are they predictive? Is female, if it's true, it's a 1, and if it's false, it's a 0. So it's a high, that means each of these dots was a row, and is female was true in this case or false in that case. With respect to the SHAP values, increasing means a better chance of survival. So if is female is true, I think all the records say that if is female is true, then there's an increased chance of survival, and sometimes quite a high increased chance of survival. If is female is false, then most of the, all the examples give a smaller contribution to chance of survival decreasing. So if you're a male, there's a good chance that you will be less likely to survive unless some other feature increases your survival rate. P-class has a similar result. If P-class is low, so low is blue, low is 1, so if you're first class, you have an increased chance of survival. If P-class is high, third class, that means you're in steerage down below, you have a decreased chance of survival, but a lot of it clustered around the 0 point, so not having a huge impact. Whereas is female has this massive impact across the board. Age imputed, a lot of clustering around the center, but if your age imputed, your age is very low, like the 9-year-old child, typically there's a much higher chance of survival, so that's kind of interesting. Sibling, spouse, parents and children, almost all the results are clustered around the 0 point, but if you had a high count of siblings, spouses, parents and children, then your chance of survival decreases. So that's a lopsided contribution to whether you survive or die. So, and there are some further pots that Shapley brings out. It's very young, this tool. It does work. You need to use the Git master version. The published version on pip is a bit busted in notebooks. Definitely recommend you give it a go. The documentation's a bit light, but I think the results are really interesting. And Tobias tomorrow is talking on Eli 5 and Lime, so if you're interested in this, I suggest following up on that talk. So, closing, I think everyone should be diagnosing their machine learning just like they debug their code. Particularly if you can't explain the working of your machine learning model to a colleague, particularly a non-technical colleague, then I believe that we don't understand what this model does. And black boxes are cool for winning Kaggle competitions. They're not cool for having robust, reliable, engineered solutions in the workplace that we need to keep maintained after we've gone. So we have to be able to debug and understand these things, and these tools begin to let us do that. I give training and coaching on this kind of stuff. If that's interesting, talk to me. There'll be a write-up on this on my blog. There's a write-up from PyData London from a month ago, and I'll be posting the code up onto Data Science Delivered on GitHub shortly. I love talking about this. You can buy me a beer if you want, but I just love talking about this stuff. But do buy a beer or a coffee for the fellow volunteers here, please. But I do have a request for you, a very serious request. I realized that after 7 years talking, about a year ago I realized this, I'd never asked for anything back in return. And it turns out I like receiving postcards. So I now have a small collection of postcards up in my office that remind me that when I volunteer and put time in, people like this stuff, and then I get a postcard sent to me from an interesting place on the planet. So if you've learned something and you want to send me a postcard in the future, I'd be super happy. Just send me an email, I'll send you my address, send me a postcard. I don't care when or where from. I just like receiving postcards. It makes me happy. So please do that. And that'll be it. Thank you very much.
So in terms of paying for coffee and beer to people that you appreciate, I just want to announce that indeed the beer tonight is free. So, we are now between this moment and coffee.
Okay, we should do coffee.
I think there should be at least one or two questions that are relevant to the entire crowd before we have coffee. Does anyone have a question? Yes.
All right, I'll take just 2 questions and then we can have coffee, because I think morning coffee is important.
Thank you. It was a really great presentation. So my question is about the first part of your presentation. Do you have any suggestions for a baseline classifier for problems with heavily imbalanced classes?
Sorry, say again, do I have a solution for?
Problems with imbalanced classes.
I guess it depends on which part of the early part of the talk. The ROC curves are pretty good at diagnosing imbalanced classes.
Baseline classifiers for designing baseline classifiers.
Oh, baseline classifiers.
Yeah.
Sorry, baseline classifiers. No, you can. There are several. I think there are 5 strategies in the dummy classifier. One is stratified sampling, so it tries to reflect the underlying prior knowledge. With heavily imbalanced classes, everything you just predict. Yeah, exactly. I still think you have to do it, and I would start with, say, a most frequent, just because I get a baseline that I shouldn't be any worse than this. But yeah, no, that's a harder one. I'd be happy to talk afterwards about that, perhaps if you give me some more context about it. I think partly this advice is, I try to keep this advice general, and each time I dive off into a special problem, I realise that all my general advice is a bit guff, and I have to think again about an underlying problem and how I represent the right way to start a process. But thinking about a baseline and building up is the important bit, I guess. But sorry, I don't have a clearer answer there. Other problem?
Hello, thanks for the talk, it was fun. I had a question. I actually don't know much about the data set. You just have to predict alive or dead?
I did kind of assume everyone knows the Titanic data set. Yeah, you've got 1,000 passengers and Titanic sinks. Some people survive, some people die. Can you use their attributes to predict who will survive or die? And women and children typically survived. Rich people had a much better chance of surviving. Poor men who were middle-aged or younger typically died, and that's kind of the end result. And the Titanic film shows you that. And then the question is, can you use the data to make a similar prediction?
And you only need scikit-learn. You don't need Leonardo DiCaprio. That's great. We still have over 20 minutes to get a coffee, so let's just do one more round of applause. Ian, thank you so much.
Thank you.